Hello once again, welcome back to our Chem 151 video series. In this video we'll be talking about how to draw resonance structures and how to find the bond order of certain bonds after having drawn the resonance structures. We'll start by reviewing how to draw the Lewis structure for HCO2 1 and negative, and we'll review how to minimize the formal charges. Once we've drawn that, we'll move on to resonance structures. We'll begin by listing the atoms that are in this molecule. We'll have hydrogen, carbon, and oxygen. There's one hydrogen, one carbon, and two oxygens. Now we're going to multiply each of those numbers of atoms by the group number for each atom. Hydrogen was in group 1A on the periodic table, carbon is in group 4A on the periodic table, oxygen in group 6A. We'll multiply the numbers of atoms by that group number. So for hydrogen, we'll say 1 times 1 gives us 1. For carbon, 1 times 4 gives us 4. And oxygen 2 times 6 would give us 12. We're not quite finished yet, though, because we have to pay attention to the charge as well. Since we have a charge of -1, that means we're going to have one extra electron more than we would expect. Now we'll add 1 plus 4 plus 12 plus 1, giving us a total of 18. Now we'll begin drawing our structure by putting the least electronegative atom in the center, not counting hydrogen. Hydrogen in this class will never be the central atom. We'll put carbon in the middle, and then an H and two oxygens. This will be the beginning of our structure. Now we're going to have to bond each of these atoms to carbon. We'll connect hydrogen to carbon and both oxygens to carbon, and we've drawn 3 bonds. Each bond that we've drawn uses up 2 electrons. So we'll say 3 times -2, giving us -6. We take the 18 we found a moment ago, minus the 6, giving us 12 electrons left over. We're going to give the leftover 12 electrons to the most electronegative atoms available, and that's oxygen. So, since oxygen has 2 electrons connected to it right now, it can take 6 more. Same with this oxygen down the lower right. So for oxygen, we'll have 6 dots. So we'll take 2 oxygens times -6 gives us -12 electrons. And then the 12 we had left over minus that 12 gives us 0. It's possible that the structure we've drawn is not the most stable possible structure, so let's check the formal charges. Just as a reminder, the formula for formal charge is your valence number minus your bonds minus your dots. For oxygen, we said a moment ago that oxygen's group was 6A. Therefore, its valence number is 6. Each oxygen is connected to one bond. We're not going to count both. We're just looking at a single oxygen. And then minus 6 dots. That'll give us a charge of -1, and so we'll place a negative on both of these oxygens. Now for carbon, let's rerun the calculation. We said earlier that carbon is in group 4A. Therefore, we'll say there's a valence number of 4 minus 3 bonds connected to carbon, no dots around carbon, and so its charge is +1. We'll place a positive sign next to carbon to show that. Now, anytime you have a negative next to a positive, you can take electrons off one of the negatives and move it into the middle, as I've shown in a previous video. Therefore, the new structure will have a new double bond in the upward position, and then oxygen gives up 2 of its dots and has only 4 dots now rather than 6. The oxygen on the right still has 6 dots, though. Now let's run the calculations again. This oxygen on the right is not changed, and so it would still have 6 minus 1 minus 6 for -1 charge. So we'll put a negative sign on that still. However, the oxygen that points upward has changed. The valence number for this oxygen is still 6, but now rather than 1 bond, it has 2 bonds. So we'll say 6 minus 2, and we have a total of 4 dots. So we'll say 6 minus 2 minus 4 now gives 0, and then this oxygen is now neutral. That's more stable than it used to be. because we want neutral if possible. Now we'll check the carbon down here at the bottom. So carbon still has a valence number of 4, but now this carbon has a total of 4 bonds around it rather than just 3. So we'll say 4 minus no dots around carbon, so 0, giving us a charge of 0 for that carbon, and it is neutral. So notice that after we've made this move, there is still a negative oxygen, and that's on the right. It turns out this is okay because our original formula was HCO2 negative. So we can expect at the final structure to still have a negative somewhere. So the fact that our final structure has a negative on one of the oxygens is okay. Remember that our goal is to minimize the formal charges, but it's not necessarily always possible to get them all to 0. Now that we've drawn the Lewis structures, let's think about possible resonance structures. We can see there is a double bond between carbon and oxygen in the upward position here that I'm circling in green. Now, even though we've drawn the double bond in that position, that doesn't necessarily mean that the double bond is locked into that position. The double bond right now is between carbon and oxygen, but that double bond could be between carbon and any oxygen. Basically, the double bond doesn't care where it is as long as it's between carbon and oxygen somewhere. Therefore, to draw a resonance structure, we can draw the double bond in the other position pointed toward the other oxygen. This oxygen on the right, which was previously single bonded, can be double bonded and end up with 4 dots rather than 6 dots. And then this oxygen on the upward position, that was previously double bonded, can be single bonded and have 6 dots. And it turns out these structures are equal resonance structures. However, you could not do the same thing between C and H. The reason why is because C to H is not the same thing as C to O, and therefore that would not be an equal resonance structure. Therefore, when we draw these resonance structures, we only draw the double bond moving between the 2 different COs, not between the C and the H. Now, to find the bond order of the CO, what we're going to do is circle the same region on both structures. I've already circled in green this C to O that's pointing up. It's a double bond in the first structure, but it is a single bond in the second structure. Now, notice we have circled 2 regions, but inside of those regions, we have circled a total of 3 bonds, 2 from the first structure, 1 from the second structure. Therefore, our bond order will be 3 bonds divided by 2 regions, which means our CO bond order is 1.5, which is what we would get if we divided. So we'll say that C to O is actually 1.5 bonds. That's going to be different from the CH, though. In the lower left, you can see in both structures, the CH is single in both instances, because if we had tried to move the double bond there, that would not have been an equal resonance structure. Therefore, we'll say CO is 1.5 bonds, but CH is still only a single bond, and so there's no need to do any math for that. Because the CH does not change between structures, we know it's always going to be single, and we'll say the bond order for CH is only 1 bond. The important thing to realize is even though we've drawn a structure that looks like one of the O's is double bonded and one of the O's is single bonded, in reality what's happening is that both oxygens have 1.5 bonds to the carbon in the middle, while the hydrogen only has 1 bond to the carbon in the middle. Thank you for watching, and we'll see you again soon.